Okay, today we're going to have a look at the reverse chain rule and u-substitution. So we can use the reverse chain rule to solve many of these questions, and you'll get good at it with practice. So for example, we might notice that the differentiation of this is 4x and it's almost outside the brackets. So we times it by 4 and times by a quarter at the same time. However, until you get good at this, you're welcome to use a u-substitution, which I'm going to in all of these examples. So the integral of x cubed, x4 minus 2, the way you know it's in the form of the reverse chain rule is if the thing outside the brackets has a power or an order 1 less than this one. Now we're going to let u equal x to the power of 4 minus 2. In extension 2, I purposefully shown you how to use u-substitution even when you're not given the substitution to wheel you in for extension 2. That means du is 4x cubed. So we want to put the 4 here and the 1/4 there, and we've got a dx. So this is now 1/4 the integral of u to the power of 5 du, which is 1/4 u to the 6 on 6 plus c, which is x to the power of 4 minus 2 on 6 over 24 plus c. Okay. Example number 2, notice that the differentiation of this is almost up there, but let's use a u-substitution to confirm that. So let's u equal 4x, u equal to 2x squared minus 1, which means that's where that came from, 4x dx. So realistically, we want a 4 up here and a 1/4 there. So this is going to be 1/4 the integral of du, which is 4x, because there's a dx here, on root u. Now the integral of the square root of u is going to be 2 root u, I'm pretty sure. So 1 on 4 times 2 times root u plus c, which is 1 on 2, 2x squared minus 1 to the power of a half plus c. Okay, example number 3, the integral of e to the 3x root e to the 3x plus 1. Let's go, let u equal e to the 3x. Again, u-substitution not necessarily necessary here, because differentiate that, you get 1/3 of that, or 3 times that. So du is equal to 3e to the 3x dx. So let's put a 1/3 here and a 3 here. That's going to get us 1/3 integral root u du. Now the integral of root u is 2 on 3 times u to the 3 on 2. So it's going to be 2 on 9. And what was e to the 3x? We might say e to the 3x plus 1. Sorry, I meant to write that there. E to the 3x plus 1, 3 on 2 plus c. Done. Example 4, x sine x squared. Again, we've got to, and this is where extension 2 can get tricky. We are not told what to make u, but we're thinking, okay, if I differentiate x squared, I get x. So I've almost got the differentiation outside. So let's say let u equal x squared, which means du is 2x dx. So if we put a half here and a 2 here, we've got a half integral, that's 2x dx is du, so sine u du. Now the integral of sine is minus cos, so times minus cos u plus c. So we get minus a half cos u is x squared plus c. Example 5, the square root of cos of 2x times sine of 2x. A number of different ways of approaching this question. Often when we've got a square root in the integral, we work with u squared instead of u. It makes the algebra easy. But I think I have a whole separate lesson on that, so I'm not going to do that at the moment. So I'm going to say let u equal cos of 2x. Usually we want the thing under the square root to be u, because if we didn't, then we would accidentally get a du underneath the square root potentially. We don't want that. So du is going to equal minus 2 sine of 2x. So we want a minus a half here, I think. We want a minus a half here, integral root u times by 2 sine of 2x dx. So we've got minus a half times 2 sine x dx. That gets us minus a half times by u. If we integrate u, root u, we get 2 on 3, u to the 3 on 2 plus c. Of course, that's because this is du, if I didn't mention that earlier. So the 2's will cancel, and we actually get minus 1/3 u to the 3 on 2 plus c. And u is just cos of 2x, so it's minus 1/3 cos of 2x, 3 on 2 plus c. Okay, example 6, e to the x sine e to the x. Hopefully a nice and easy one, because if we differentiate e to the x, we get e to the x. So let u equal e to the x. That means du is equal to e to the x dx. So this is just simply the integral of sine of u to u. That's because e to the x dx is du. So this is minus cos of u, which is e to the x, plus c. Easy. Okay, they're starting to get a bit fun here. I'm noticing that we've got sine inverse of x and then 1 on square root of 1 minus x squared. I know if I differentiate sine inverse of x, I get 1 on the square root of 1 minus x squared. So I'm going to let u equal sine inverse of x. That means du is at 1 over the square root of 1 minus x squared dx. So this is just the integral of e to the u, and this dx is du. So it's just integral of e to u to the u, which is e to the u, and u is sine inverse of x. Looked scary, one of the easiest integrals I've ever done. Okay, last example for today is sine ln of x on x. We're thinking to ourselves, what do I make u? Now I'm thinking, okay, if I differentiate ln of x, I get 1 on x. So let u equal ln of x, du is 1 on x. Bam, I'm basically done. This is sine of u, and 1 on x dx is du. So this is just the integral of sine of u, which is minus cos of u plus c, and u is ln of x. So it's minus cos ln. Now, I don't remember these whole absolute value things when I did the course. They might have been there and I just wasn't taught it. But when we do ln's and integrals, we generally put an absolute value, so just get used to doing that. Okay, thanks for listening.